Okay, next question. Show that the relation divides on capital N is partial order relation. Okay, we'll prove this is a partial order relation. So, what about the relation divides on N? N is set of all natural numbers, divides on N. So, first thing to prove partial order, we need reflexive. Reflexive means we have A divides A for every A in A. That means 1 divides 1, 2 divides 2, 3 divides 3. What do you mean by divides? Remainder will be 0, right? Remainder will be 0. So 3 divided by 3, remainder 0. So here A divides A. So A related A comma A element of R. So R contains all the elements which is of this form. A comma A element of, it goes on like this. A comma A element of R. Therefore R is reflexive because the relation is defined like this. Okay, here the relation is defined and we have to write the set R. Show that the relation, what is the relation? Divides on capital N. That means 1 divides 1, 2 divides 2, 3 divides 3 will be element of R here. So now, therefore R is reflexive. First condition we have proved, okay? R is reflexive. Then let us come to anti-symmetry. Anti-symmetry means what is anti-symmetry condition? We know anti-symmetry for AB element of the set. A comma B element of N here, right? For A comma B element of N. That means A should, when it A comma B element of that relation means it should, let us write it as R. A comma B element of R means A divides B because the relation is divides on. A divides B. A divides B means definitely B divides A if and only if A is equal to B. For example, 2 divides 4. 2 divides 4. And whether 4 divides 2? No. 4 does not divide. 4 does not divide 2. So we cannot take 4 comma 2. We cannot take 4 comma 2 because 4 divides 2 because 4 divided by 2 remainder is 0. Whether 2 divides 4. Okay, here 2 divides 4. 2 divides, or I will write like this. 2. So if you divide 2 2s are 4. Remainder is 0. So 2 divides 4. But when you come to the second case, whether 4 divides this, 4 divides, can you divide 2 by 4? No. So you cannot take the other case. 4 comma 2 does not belong to R. Okay, 4 comma 2 does not belong to R because 4 does not divide 2. So what is the only possibility here? If I take like this, 2 divides 2. Even if you interchange 2 divides 2, that means A is equal to B. Case is only possibility. If you can take 4 divides 4 and here A is equal to B. That's the only possibility. That is A divides B implies B divides A means A should be equal to B. All the other cases it is false, okay? For example, just now I told 2 divides 4 but 4 does not divide 2. So that 2 is equal, we have to prove A is equal to B, right? So only possibility A divides B, B divides A means the only possibility is A should be equal to B. Like this, okay? 2 divides 2, 2 divides 2. A divides B, B divides A means A is equal to B is the only possibility. Therefore, it is anti-symmetry. This is definition for anti-symmetry, right? Anti-symmetry we have learned for a partial order set. Anti-symmetry means A related to B, A related to B, B related to A implies A is equal to B. Okay, A comma B element of R and B comma A element of R implies A is equal to B. So here this is true, therefore relation R is anti-symmetry. Now coming to the next case, what is the next case? Transitive. Is it transitive? What is transitive? For A, B, C element of N, A divides B, B divides C, then A divides C. For example, let me take like this: 2 divides 4, 4 divides 8, then automatically this implies 2 divides 8. Okay, we can say A divides B and B divides C implies A divides C. So A divides B, B divides C implies A divides C. So for example, I have given 2 divides 4, 2 comma 4, 4 divides 8, 4 comma 8, then 2 divides 8. So this belong to R means then this also belong to R because 2 divides 8. Therefore, R is transitive. So if it satisfies this condition, we say it is A comma B belong to R, B comma C belong to R implies A comma C belong to R. So here this is true because divides A, if A divide B and B divide C, definitely A will divide C, then A comma C will be there. AB in R, B, C in R, then AC will be in R. Therefore R is transitive. So here all the three conditions are satisfied. What is those conditions? Reflexive, antisymmetry and transitive. So since these three conditions are satisfied, relation is a partially ordered relation. Given relation is a partially ordered relation. Okay. Next definition, partial ordered set. Okay, partial ordered set. What is partial ordered set? Partial ordered set, or we call it as poset. Okay, poset, partial ordered set. A set capital A together with partial order relation. What is POR? You can write it as partial order relation. A set A together with partially order relation capital R on this set is defined by, okay, on this set is defined by A comma R. So A comma R or A comma, for example, A comma greater than or equal to. If you have greater than or equal to, where greater than or equal to is a partially ordered relation, then we say A is a partially ordered set. Okay, a set A together with a partially ordered relation is called as partially ordered set. So if greater than or equal to, here is a note, you see, A is greater than or equal to A for any integer A. So we consider integers for any integer A. Therefore greater than or equal to is reflexive. Greater than or equal to is reflexive. Then A greater than or equal to B, B greater than or equal to A, then A is equal to B, right? 2 greater than 1, then here you see 1 greater than 2. We cannot write 1 greater than 2, right? This is wrong. So we cannot write like this. So you can write equal to condition will be only true. 1 greater than or equal to 1, like that you can write. So here the possibility is 1 is equal to 1. So always A greater than or equal to B, B greater than or equal to A implies A is equal to B. Okay, A will be equal to B. Therefore it is anti-symmetry. That is called as anti-symmetry condition. A related to B, B related to A, then A is equal to B. A is equal to B. So just now we learned, right, poset. We learned partially ordered relation. Partially ordered relation means reflection should be true. Anti-symmetry should be true. Anti-symmetry means A related to B, B related to A means A is equal to B. Then transitive. This is transitive, okay. Transitive should be true. That means A greater than or equal to B, B greater than or equal to C, then A greater than or equal to C. That is true, right? If 5 is greater than 4 and 4 is greater than some other element, we can take like, just a second, we'll consider an example like, we'll take 3 here. 5 is greater than or equal to 4, 4 is greater than or equal to 3, then it's here 5 is greater than 3, right? 5 is greater than 3. So that's what here, A greater than or equal to B, B is greater than or equal to C, then A is greater than or equal to C, then it is transitive. So this greater than or equal to is a partially ordered relation. Okay. So here it is defined like this. A set A together with a partially ordered relation capital R on this set and is denoted by, okay, and is denoted by A comma R. Thus A is the set and R is the partially ordered relation. That relation can be anything greater than or equal to, or just we learned example like divides, right? Divides, whatever it is, the relation a set together with the partially ordered relation is called as partially ordered set. Next definition, totally ordered set. If every element of, okay, we say it is a totally ordered. If every two element of a poset P less than or equal to, okay, we have learned what is poset. So if every two element of a poset are comparable, then P is called a totally ordered set, or otherwise called as linearly ordered set. Okay, comparable. So how will you compare? We can say 2 is less than 3, okay, or 3 is greater than 2, so or equal to, like that. So if it is comparable, any two elements is comparable, then we say it is a totally ordered set. The totally ordered set is also called as chain, okay, chain. The totally ordered set is also called a chain. That means in a chain every two elements are comparable. In a chain every two elements are comparable. Here is a question. Show that the relation less than, okay, less than, relation is less than defined on n, defined on natural numbers n, the set of positive integer, okay, here it is defined, n is defined as set of positive integer. We take only the positive integer here. Is neither an equivalence nor a partial order relation, but it is a total order relation. Is neither NEI, neither an equivalence nor a partially POR partially order relation, but it's a total order relation. Okay, so we have to prove it is not equivalence, not a partially order relation. So let us come to the answer. Answer is let A belong to n. A less than A is not true. Is it true? A less, because here the relation is less than. Okay, here relation is less than, but A less than A is not true. Therefore, reflection is A or is not reflection. When it will be A related to A, then only it is reflection. But here A is not related to A, because the relation is less than. We cannot tell A less than A is not true. So not reflection. Then less than is, therefore less than is not an equivalence relation nor a partially ordered relation. So we know that if it is not reflexive, reflexive is the main condition in for equivalence relation also first condition is reflexive. For partially ordered relation also first condition is reflexive. Here it is not reflexive, therefore it is not a equivalence relation, not a partially ordered relation. But for every A and B, either A less than B or B less than A or A equal to B. Therefore, it is a total order relation. Total order relation means every element is comparable, right? Just now we learned every element is comparable. That is, A will be less than B. So here when you come, set of positive integers. Integer means either 1 is less than 2 or 2 is greater than 1, like that. So either A is less than B or B is less than A or A is equal to B. Therefore, every element is comparable. We can compare, that is definition for total order relation. So we say this relation is a total order relation. Okay, that's the solution. Hence we have proved.